generate in symmetrical molecules. So my talk is organized in 3 parts. First, I want to speak about rather old work that I did with mainly with Berlin and Litschi in Mainz, where we formed long-lived spin states in dimethyl malate by parahydrogen, and then work that we also did in Mainz together with Barbara, James, Marcus, and Megan Levitt, where we generated hyperpolarized long-lived fumarate by PHIP. And the last part of my talk will be driven by a really big community by a big team coming from the university in Darmstadt and from Southampton, from the Budga group in Mainz and many other people from Torino, but the main co-workers here were Stefan Knecht and James Eins. Okay, so if we have long-lived spin pairs, if we want to have them, we make use of singlet spin states, because here many relaxation pathways that we have in normal NMR don't occur. But to have them, we need a strongly coupled two-spin system. So if we have an inequivalent pair of spins, normally our split in our chemical shift is much larger than the J coupling. And that's then called a weakly coupled system. And there we won't have a singlet state. So if we use a chemically equivalent pair of spins, of course, the difference in the chemical shift will vanish, and the J coupling is larger than the chemical shift difference at any magnetic field strength. And there we have what we call a strongly coupled system. And here the singlet state is an exact eigenstate of the system that's immune to the normal relaxation mechanism of dipolar coupling. Therefore, it is long-lived. But we have, as we had heard already many times during this meeting, the problem that the singlet spin states are NMR silent. So we need to convert them to triplet states to measure them. So, of course, parahydrogen is a perfect source of hyperpolarized singlet spin states, because parahydrogen already possesses the required singlet symmetry. If we now insert parahydrogen into a symmetry breaking environment, we automatically convert the singlet state to a triplet state and can observe our normal Pasadena signals. However, if we do that and maintain the sample at a very low magnetic field, where the chemical shifts where the split in chemical shifts is very small, we can still have here a singlet state at low magnetic field. However, if we insert our parahydrogen into a symmetric molecule, where here the two rests R1 and R2 are the same, then we can have chemically equivalent spins at all magnetic field strengths, and our chemical shift is maintained. Our singlet state is maintained for all magnetic fields. And we were very much interested in working with PHIP in that symmetrical molecules, just to be able to maintain the singlet state at all magnetic field strengths. So our working horse at the beginning was this molecule. This is dimethyl malate, which you can where you can parahydrogenate this precursor, and then you have the spin system where you have here the two former parahydrogen protons, and we have here only two chemically equivalent spins because they have different J couplings to the methyl groups. And this is very nice because that allows us to make use of singlet triplet level anticrossings for the singlet state readout. We heard already a lot of the use of level anticrossing in these type of systems, and we use them, of course, also. And you can calculate a field strength where that level anticrossing will appear and where you are able to convert your singlet state into an observable triplet state. And in this molecule, that is at the point at the field strength of 0.1 Tesla. So how we do the measurement, we just prepare our sample and put parahydrogen to the precursor, shake it, and then we just acquire a spectrum. And there the vinyl protons are in the singlet state, so we can't observe them, but we see the peak of the methyl protons. Then we lift our sample to a position in the stray field of our magnet where we have that 0.1 Tesla, and the single triplet conversion can occur. And once you then put your sample down to the coil again, you measure again a spectrum, and now you see that hyperpolarized signal from the vinyl protons. And by this technique, of course, if you vary the waiting time, where you just let your sample sit in that magnet, you can measure also the lifetime of your single state. And we did that, and that requires preparation of many samples and then measure them with the different waiting times. But the experiment still worked quite well, and we could measure the singlet state lifetime of the system to be roughly 4 minutes. Of course, it's a little bit bad if you have to move physically your sample around, and you can have the same effect by applying a pulse sequence where you just let your sample think that it is sitting at 0.1 Tesla, and you can have that by working with chemical shift scaling pulse sequences. And the sequence looks like that, and then you just acquire your FIDs over time, and you can fit that, and with that you end up with the same singlet state lifetime of the system of 4 minutes. You can then go ahead and just, let's say, use your antiphase magnetization that you have now in the triplet state and perform imaging experiments, which we did also in the medical scanner. And here we just vary the echo time to see different contrast in the images. And that is due to the fact that at a certain echo time, you have a positive interference due to chemical shift difference and J coupling of your spin vectors in the XY plane. We published that in another paper before. So all this was wrapped up in a contribution to Giuseppe Pileo's wonderful book of long-lived nuclear spin order. And because here so many people are working with long-lived spin order, so I really highly recommend this book. So as a conclusion for the first part, we have seen that D-methyl malate works nicely for PHIP, and we have a very nice singlet state lifetime of 4 minutes. But in a symmetric molecule without level anticrossing, the singlet state lifetime should be even longer. And then we thought, okay, let's take the methyl group off. Then we end up with a molecule that is called malate, and they don't have a level anticrossing, which we want, but unfortunately it is toxic. And we very much wanted to work with molecules that can be applied in vivo for medical MRI, but that molecule would be the trans-isomer fumarate, and that of course requires a PHIP hydrogenation reaction in transposition. That brings me to the second part of my talk, where I work with Barbara, James, Marcus, and Malcolm Levitt. Okay, so when we started to do that work, we had just a very lucky coincidence, because we were searching in the literature about a transhydrogenation catalyst, and then Markus Leutsch came to my lab in Mainz to visit us and to learn something about PHIP, and he worked in the Fürstner group, and they are really experts in hydrogenation catalysis, and of course they knew also catalysts that can hydrogenate in transposition. So he immediately could recommend us the right papers, but then we have still a lot of work to do from the many catalysts mentioned in the paper to find the right one. And also all of them were not tried in D2O, of course, but after really a long time of trying around, Barbara got the trick of it, and she could see the first hyperpolarized fumarate. However, the conversion was really, really low. And then we were thinking, what can we do? And at some point, we just put oxygen scavengers to the sample. And one of them was what James is always calling the magic dust. That is sodium sulfide. And with that, immediately, we have a much higher conversion, but we have no clue why. Why is that? So maybe the people of the Fürstner group have to go back and have to find out what does the sodium sulfide to this chemical reaction. I don't know. But at least now we had a reaction where we can really work with, because now it is fast and it's almost complete. Okay. Of course, we started to work not with a non-labeled fumarate, because then we have our parahydrogen directly in the singlet state, and we can't read it out, and we can't optimize something on that. Of course, we put a spin label of carbon-13 here to make the two protons in the fumarate just chemically equivalent, and to have a level anticrossing, and therefore a mean to read as a singlet state. So a level anticrossing in the carbon-13 labeled fumarate is as roughly 420 nanotesla. And we achieved that condition just in a mu-metal shield. And then we got polarization transfer and then enhanced carbon-13 in the fumarate. Of course, it is much more elegant not to do it again, which was a field cycling technique, but with a dedicated pulse sequence. And James and Michael Levitt, of course, experts in the technique. So we used their conversion sequence for singlet order to heteronuclear magnetization. And we used the pulse sequence, and then we ended up with a highly polarized carbon-13. So in that days, it was not that highly polarized as we can do it now. Okay, but at least we could do we could generate a hyperpolarized carbon-13 fumarate, and we could also measure the singlet state of that. And of course, because we have still the level anticrossing, the lifetime is not that hard, and it depends heavily on the amount of oxygen that you have in your sample. Okay, after now we got some experience with the system, we could go on with a non-labeled fumarate, but here, of course, we need a readout mechanism for the singlet state. And that we can easily have with fumarate if we just make a bioconversion with an enzyme that is called fumarase, and then malate is formed. And of course, in malate, the two former parahydrogen protons have a different chemical shift, and so we have them in the triplet state, and we just acquire a normal Pasadena spectrum. This technique was already used before us by the Janin group, who polarized a fumarate via a dissolution DNP. So with the enzymatic readout reaction, we didn't really measure the lifetime of the fumarate. We just have a quick guess on it. So if we observe our spectrum directly after the addition of fumarase, we see here a high malate peak, and after 30 minutes, we still can observe a tiny malate peak. So at least we have still signal on the protons after 30 minutes. Now that means that the lifetime must be at least 6 seconds. And that corresponds very well to data measured from the Yershov group, who measured dimethyl fumarate with a fully deuterated methyl groups, and they had a TS lifetime of 350 seconds. So that fits. Okay, as a conclusion of that part, we were able to generate the hyperpolarized fumarate, and we found a long TS time of the protons. Of course, there are still some problems with the chemical reaction, like over-reduction or a small fraction of malate is formed. And also we have some leakage of the hyperpolarization due to the formation of the ruthenium carbines, where Markus Leutsch talked about yesterday. Okay, but we have a very encouraging singlet state lifetime of fumarate. So with that, I come to the third part of my talk, where we work with a really big team of fantastic people that was led by James and Stefan Knecht, who really did the main part of the work. And here the idea is the same as I told you before. So we convert fumarate enzymatically to malate and then use a special imaging sequence to only measure the malate protons and not the thermal background. Okay, and that may overcome the problems of using protons in hyperpolarized MRI. Of course, it would be very nice to measure protons in medical hyperpolarization experiments, but the vast thermal backgrounds that we have normally is still much bigger than our hyperpolarized signets. And of course, if we polarize a component on protons, we normally have a short T1 time, and that also prohibits the medical application. However, if we use, like we have it in fumarate, protons that are in the singlet state and have a long lifetime, like we have in fumarate, we avoid the problem of the rapid relaxation of the hyperpolarization. For the proton background that we have in vivo, so water and fat, that can be saturated with RF fields, and the non-magnetic singlet state of our fumarate would remain unaffected. And for the lag in chemical shift dispersion, so normally in carbon-13, of course, we have a much larger range of chemical shift, and that's very nice if you have to look for broad peaks in vivo. And a lag in chemical shift dispersion could be a really drawback, but in our system, we are just looking for peaks that are appearing and not shifting. So the fumarate we can't see at the beginning at all, and then just the malate is appearing. So what do we see in a malate spectrum? So if we have hyperpolarized fumarate in the singlet state in water, of course, we will see the polarization in the water, and here a red background means that we can see these spins, and fumarate in the singlet state with a gray background we can't see. Then we transfer it to malate, and now we can see already also the antiphase magnetization with the malate. And that's the resulting spectrum. So we have here a big large water peak, and then we have the normal Pasadena spectrum of malate. And the PHIP sequence was designed to rephase the antisignets for MRI. I asked Stefan and James just to do it with optimal waiting time in the imaging sequence, but of course they want to do it perfect. So they designed a sequence to do that. And of course, we want to remove the thermally polarized background. Okay, so they designed two PHIP sequences. One is called OPE45. And I just quickly show the PHIP sequences here. That is based on a hard 45-degree pulse, and then the background signal is destroyed by the last gradient pulses here. Or we just chemically selectively excite one of the malate peaks and then work with that select D90 pulse sequence where we don't excite the background at all. So the experiment looks like that. Of course, we hydrogenated the precursor. We got hyperpolarized fumarate in singlet state. And then we just shuttle everything through a tubing into our NMR tube where the enzyme solution is already waiting. And then we just have a tube guide inside that. And so I was always afraid that it don't mix properly, but because we shuttled quite fast, I think the mixing was quite okay. And then, of course, the fumarase will convert our hyperpolarized fumarate to hyperpolarized malate, and where the protons are then at the triplet state. And then we see how the spectra look like after an acquisition only with a 45-degree pulse, where we just have the normal Pasadena spectrum, and that here is the acquisition with the OPE45. It looks really similar to the simulation we have seen before. So we have here still a very tiny signal of the water, and with the selective 90-degree pulse, the water is fully suppressed, and we have a nice signal of the malate spins that we are so excited. Okay, with that sequence, we were going to another penta, and there, of course, we need some thermally polarized background signal. So we put our PHIP tube just inside a kind of water bath. So that was a tube with a 30-millimeter outside, just filled with normal water. And inside here is a tube where the enzyme solution is sitting, and we have here a small capillary that reaches down to the bottom where our PHIP solution is injected. Okay, and then just the OPE selective 90 sequence was applied together with a centric reordered flash readout for the imaging part, and then we got these images. So that's just the normal image of the phantom, and that is with the sequence applied, and you can see here that we fully suppress the water background and see a nice signal of our hyperpolarized malate, and that tiny dot here is just the tube for the injection of the PHIP solution. Okay, and of course, you can now acquire also a time series of images, and of course, your signal decays because the singlet state decays, and of course also the fumarate concentration is decaying, and therefore also the concentration of malate. Okay, and with that, we have seen that the single contrast MRI had really nicely worked in that phantom. But I think that the usefulness for medical MRI depends now strongly on the lifetime of the fumarate singlet state in vivo, and we don't know it yet. But we have a strong feeling that it might be too short for a real in vivo application and a real proton detection for the metabolism of fumarate. So maybe polarization transfer might be the better option to work with hyperpolarized fumarate, but I still think that generating it via PHIP is a better option than doing it by dissolution DMP. And that is also because Stefan and James had showed that they can really rapidly purify our PHIP solution of the fumarate by precipitation of the fumarate, and we can take all the catalyst and precursor or side products out of that and have a neat solution of hyperpolarized fumarate with a high polarization at a dedicated concentration. And yeah, that was just some advertisement for the talk of James that you will hear later. So with that, I just want to thank many nice co-workers, and especially all the people from the newly formed dream team around Stefan and James, and the funding sources, and you for your attention.
Thank you so much, Dr. Kerstin. This is very beautiful presentation. Thank you so much. We will go to the question session now. So if you have any question for Dr. Kerstin, you can post it on the Q&A. So we have the first question here by Alexi. Says, Dr. Kerstin, beautiful talk, thank you. I was wondering whether you saw any evidence for proton transfer to affect lifetimes.
So you mean if we transfer the fumarate proton to somewhere else? So I think I didn't get the question right.
I think the question means, like, is there any evidence for proton transfer affecting lifetimes?
So normally what we see is after we have now worked a lot on the chemical reaction, that the reaction is very, very fast and complete after a few seconds. So I think that it doesn't depend very much the lifetime then on the bubbling rate and things like that. So I think we are already over that step, because the reaction can be driven to completeness in a few seconds.
Thank you so much. I guess as a follow-up to the question, is there any, do you expect to see any effects of change in lifetime of proton with regards to different tissue environments in the body?
I really think that the lifetime of the proton singlet state will be heavily affected by oxygen, for example, because we see that already in our first experiment where we had the carbon-13 label inside the molecule, and there we see already a great effect if we degas or not degas the sample, and the proton singlet state lifetime was already half if we didn't degas the sample. So I'm afraid actually that we will have, if we have desoxyhemoglobin, which is also important for the Bolt effect and stuff like that, that will further reduce the singlet state lifetime. But I really think that the T1 time of the carbon-13 spin label in the fumarate is not that heavily affected, and the T1 time of the fumarate on the carbon-13 is already also around 60 seconds, so that could be enough to perform already studies on metabolism.
Thank you so much. There's a question from Saba. It says, do you observe any singlet relaxation effects in fumarate due to proton deuterium exchange at the carboxylic sites?
So we see, of course, you see effects if you don't work in deuterated water, right? We don't. So we see that also on the lifetime of the singlet state. So it's bad if you go to the protonated solvent, and also, of course, we very much change not the spin system of fumarate, but of the conversion product of malate, because we did the experiments in D2O, and there we have a really the perfect two-spin system, and then of course if we put further protons inside, that would have an effect, of course.